Okay, hope you guys are still following along at home. I know we got a lot of dense information here. Hopefully you'll see where this maps out. We're on number 5, neurochemistry. So, neurochemistry is about how neurotransmitters are made. Do you know anything about neurotransmitters? Those are basically the chemicals that allow communication to happen all the way up to our brain. And basically what occurs, if you're not familiar with it, is the electricity from the action potential comes down to the end of the neuron, the end of the axon, and then, through a series of steps, basically causes the release of these chemicals to go across the synapse, the gap, and attach to the next receptor, the dendrites of the next neuron. So the electricity comes to the end, causes the release. The electricity doesn't generally travel across the synapse. The chemicals travel across it. The chemicals bind. And then after the chemicals bind, then the electricity of the next neuron is changed and another action potential might happen. So the purpose of this presentation is to talk about how these neurotransmitters are created, what they do, and kind of the lifespan of the neurotransmitter. So this is the field of neurochemistry. First, there are many different types of neurotransmitters. You may be familiar with some of them. Probably the most familiar one to a lot of you will be serotonin, which is very much implicated in depression. I've printed out a couple of pictures, I think, of serotonin, how it's actually made, how it actually works. Serotonin comes from the Krebs cycle, part of organic chemistry, and we're not going to go into too much detail, but you can get serotonin precursors from your diet. Tryptophan is a precursor, and basically the first step in neurotransmission is you've got to make the neurotransmitter, so it's synthesis. Serotonin is made from the diet, from tryptophan, which you can ingest, and eventually it'll be converted into serotonin. The chemical name for serotonin is sometimes called 5-HT, 5-hydroxytryptamine. Other neurotransmitters are shown on the other slide. I think I've got another slide here with the catecholamines. You've got products like dopamine, norepinephrine, and epinephrine. They are all neurotransmitters related to each other. They are based on taking tyrosine in from the diet. The brain converts them into dopamine, norepinephrine, and epinephrine. A couple of other important ones for you that we'll talk about a little bit later. Glutamate and GABA, G-A-B-A. So there are over 50 neurotransmitters, and we're not going to have to know all of them here, but you can know what they are. And so step 1, as far as neurochemistry is concerned, is synthesis. You have to make the neurotransmitter, and a lot of those comes from the diet that we eat and the products that we eat that are then converted into these neurotransmitters. Now, could you actually bypass this step and just eat a neurotransmitter, serotonin, dopamine? The answer is actually yes. But the answer is, even though you could eat it, it wouldn't do you any good. There is something called the blood-brain barrier, which I think I have a picture of as well. So if you just eat serotonin, it's not going to get into your neurons in your brain because the molecule is too large. So the blood-brain barrier is a barrier when blood goes through your brain to block large molecules, because large molecules are sometimes bad molecules, and thus you can eat these products, but they won't help you. It's better to take in precursor chemicals that are converted, synthesized into the neurotransmitter right in the neuronal area. So step 1, synthesis. You got to make the product. Step 2, they have to be stored. Neurotransmitters are stored in specialized compartments called vesicles. There are a lot of pages on this. Looks like page 120 shows pictures of the vesicles here. Vesicles are basically little packets that contain the neurotransmitter at the very end of the axon. They're often called, in the area called the presynaptic area. They're at the end of the axon before the synapse. So neurotransmitters are stored at that point in the presynaptic area. So that's step 2. You got to store them. Release. Release is very interesting. I've got a little picture for you. The name of the process is actually called exocytosis, and page 121 does actually a very nice job of saying some important things. In order for a neurotransmitter to be released from the synapse or from the vesicles, electricity has to come down from the action potential. So in that sense, we say that the release is electrically dependent. These are where the two stories meet up. When we finish the electrophysiology story, the action potential is coming down the axon. When it gets to the end, it causes the release of only a small portion of these neurotransmitters that are stored in the vesicles. So it'll be released. The name of the process whereby the vesicle that has the neurotransmitter releases it, it's called exocytosis. Now break that word down just a little bit. Exocytosis stands for exo. Basically what happens is the membrane of the vesicle fuses with the membrane of the neuron and releases the neurotransmitter. So it's called exocytosis. So step 3 is release. You got the picture there. Page 121 does a nice job of sharing that. You need to have electricity there. The other thing that the book says, which is true, is you need to have calcium there as well. So we have calcium and electrically dependent exocytosis. A lot of big words there. So those are the first 3 steps of the neurotransmitter process, the neurochemistry. Step 4 is after the neurotransmitter is released, it goes to the other side of the synapse and it binds. Unfortunately, there's a whole lot of detail on how this binding works because we can many times manipulate this if we're in the field of neuroscience. Your book actually does a nice job of actually describing some of the binding here, I believe. Turn to page 125. It has postsynaptic receptors. There are 2 types, and I've put a few pictures up for you but your book on 125 does a good job with it. When a neurotransmitter binds, it can bind to one of 2 different types of receptor. Receptor is just a small spot on the surface of the next neuron, on the dendrite. It can bind to what's called an ionotropic site, or it can bind to a metabotropic site. Good thing you don't have to say these words, huh? An ionotropic site, what basically happens is the neurotransmitter is released, it binds, and then it opens up a channel. If you look at a figure, you can see the neurotransmitter binding, and in certain cases, when a neurotransmitter binds, for example, if the neurotransmitter is glutamate, glutamate will bind and open up a channel, and when it opens up one of these ion channels, it actually allows calcium to come in. So step number 4 is the neurotransmitter binds. It can do so ionotropically, which is where the neurotransmitter binds and immediately and quickly opens up a channel. The other mechanism is called metabotropic, where the neurotransmitter binds and then it takes a little more time. A second messenger is sent out. Maybe it says a second messenger, and the second messenger opens up a channel a little bit away from where the neurotransmitter binds. This is called metabotropic because this takes more time to happen, but then when a channel is opened, it stays open longer. So we have ionotropic and metabotropic mechanisms of channel opening. So the neurotransmitter is the thing that binds, but once it binds, a channel is open, and just like we talked about before, when a channel is opened, different ions come in. And so what I want to do for you, actually I got to share the next part, then I'll give you a little summary story here. The next part, actually I got to do this with an example. The next part, let's pretend that we're working with a neurotransmitter known as glutamate. Are you guys familiar with glutamate? Monosodium glutamate, Chinese food? Well, we know that when people have glutamate in their bodies, which they do, when glutamate is released after an action potential and it binds, glutamate in almost all situations binds and opens up via an ionotropic mechanism a calcium channel. So if you're glutamate and you open a calcium channel, what almost always happens for calcium is calcium almost always rushes into that postsynaptic neuron. Now if you're calcium and you're rushing in, what is that going to do to the next neuron, to the dendrite? Calcium is Ca++. Well, if there's a calcium influx, the next neuron is actually going to get all these positive ions, and so what will happen to it? It will have an action potential. It's going to get a lot of excitatory postsynaptic responses. That's the term, excitatory. Postsynaptic responses, which means the neurotransmitter will bind glutamate, open up a calcium channel, calcium will rush in, that next neuron will have an electrical charge, it's called an EPSP, excitatory postsynaptic potential and probably fire another action potential. And we know when glutamate binds, this is what happens. The other type of mechanism that I put on the chart here, and this would really be kind of step 5, if you will, is let's say another molecule binds like GABA, G-A-B-A. When GABA binds, it'll also work ionotropically, and GABA, when it binds, will open up a chloride channel. Chloride is Cl-. And when it binds, chloride will rush in, Cl-, and actually that will tend to cause more negative charges in the next neuron. So the next neuron is going to actually not have an action potential, so we call GABA binding and chloride rushing in, we call that an IPSP, inhibitory postsynaptic potential, and when GABA binds, you tend to stop having action potentials. So the neurotransmitter binds, and on the basis of whatever channel is opened, you're going to have differential effects. The electricity will cause things to happen or not happen, and another action potential will or won't occur. So this is binding. I put some videos in here, so you might want to watch them and figure out what's going on. The last step here, and it's an important one as well, is what happens after the neurotransmitter acts. Well, we have inactivation. And actually your book does a nice job with 125, 126. Inactivation is the last step, and there are 2 ways pointed out on 126. Enzymes can come in and actually destroy the neurotransmitter, break it back down. So that's called enzymatic degradation. The other thing that happens is almost kind of a recycling type of element. Sometimes the neurotransmitter, after it binds, will be taken back up presynaptically. It's called reuptake. It's like it's recycling the neurotransmitter. So what we have covered in this particular presentation is the pharmacological basis of neurochemistry. Neurochemists study exactly how neurotransmitters work. Many times they work a lot with the electrophysiology, but how do you make a neurotransmitter? How does it get stored? How does it get released? How does it bind? And once it binds, it'll end up changing the electrophysiology of the next neuron and probably cause another action potential or not, and then its means of inactivation. That's what a neurochemist studies. So hopefully in the 12 minutes here, you have figured this out. If you need to listen to this again and use your book and use the videos, hopefully that will help you. Thanks.